3 over u is equal to z. And now let's save this expression as well. So notice that we have an equation in terms of
$1 million to whoever dares to solve my gauntlet of Lagrange multipliers. You better learn them, and you better learn them fast.
First I lost the competition, now this. What am I gonna do? I gotta figure it out.
How's that $1 million question going, Gukuji, you improper integral?
When the markers hit the whiteboard, we'll see who's laughing then.
Whatever, Gukuji. We'll see who's laughing when we have the prize money and you're still learning Riemann sums.
Oh! That was stupid.
Wake up, you must. Impressive calculus this is.
What? But I didn't even do it right.
Recognize this problem, I do. Many eons ago, written it. I have. Yes.
But that's impossible. Mr. Shulman wrote this problem. You're just some old bat.
Learned it, little Eric did. Taught him well, I have.
You taught Mr. Shulman? Who are you?
The wizard of Wiz, I am. Help you, I want. What I want, I get. Up, you get. See it here. Very close you were.
Please, Mr. Wizard, I need to solve this problem. Calculus is the most important part of my life. Please help me.
Be not so hasty. Plenty of time to learn there is. Plenty of learning to do there is. Tell me, young one, called what are you?
My name? I'm called Aryan Mukherjee.
Come, much learning of Lagrange multipliers to do there is yet.
Holy discontinuity, did you hear that?
That's the guy who taught Mr. Shulman. If he helps Gukuji, there's no way we'll win the $1 million.
Don't worry, I think we can figure something out.
3 hours later.
Homeless no more I shall be.
Alright, enough. It's pretty clear to me now that you're not trying to teach me anything, and I'm just here to do your busy work.
Yes, young Mukherjee. Time to learn more it is. For your simplistic mind, change to a more basic syntax, I will. First, we must define some terms. I assume you are familiar with the definition of a function.
Yes, it takes in a variable as an input and outputs some set of operations involving that variable, correct?
Yes, but a function could also be defined as a multivariable function, in which it takes in multiple variables as inputs, and its outputs can be modeled in multiple dimensions.
By multiple, you mean 3, right?
3, 4, 5, any amount.
Dang, that's trippy. Okay, keep going.
So first, I want to introduce to you the idea of a partial derivative. as an introductory example, how would you take the derivative of x squared?
That's easy. It's just 2x.
Correct. Now let's say you have the multivariable function f of x comma y is equal to x squared y. How would you take the partial derivative with respect to x of f of x comma y? Incorrect. What we mean by partial derivative with respect to one variable is to treat the other variable as a constant, and take just the derivative of the variable you are interested in. We use a calligraphic form of the letter D to represent this.
So the partial derivative with respect to x of f of x comma y would just be 2xy, and the partial derivative with respect to y would just be x squared?
Correct. Excellent work, young one. Now, on to Jacobian matrices.
Hey, I think I had a friend named Jacob once, but he went into humanities, so we don't talk about him.
So a Jacobian matrix is just a matrix where each entry is the first order derivative, aka the first derivative of a vector-valued function with respect to each variable present. For example, if we had the function f of x comma y comma z is equal to 4xy sine z, then the Jacobian matrix, which would only have one row since the vector is one-dimensional, would be 4y sine z, comma 4x sine z, comma 4xy cosine z.
Oh, I get it. You took the partial derivative with respect to each variable and inputted it into the row of the matrix. But come on, man, where's the punchline?
Patience, young one. You will see eventually, but you must understand. Understanding is the key to mathematics. The final thing that I would like to teach you is transposing a matrix. This is simple. You can think of transposing a matrix as reflecting it along its diagonal. Thus, transposing this matrix would simply be this. What we have now, the transpose of the Jacobian of a vector-valued function, is known as the gradient vector of the original function, indicated by this neat symbol.
Interesting.
Indeed, and what is particularly fascinating about gradient vectors is that they point in the direction of steepest ascent of a function. For example, if you were on a mountain and your mountain was represented by a function, then the gradient vector would point towards the top of the mountain in the direction that would be the most steep to climb. Remember, because we have only been dealing with one-dimensional vector-valued functions in our examples thus far, the function doesn't necessarily need to be a vector-valued function, because it could easily be turned to such as hence. For any function, multivariable or not, we can find the gradient vector for that function, and it will tell us at any point where the steepest direction of ascent would be.
I see. That means that the gradient of a function would be flat at its highest point. So we can just find where that occurs, and then we'll get the max and solve the $1 million problem. Yippee!
Not so fast, young one. This problem asks for absolute minima and maxima. And just like how in single variable calculus you had to check endpoints, the same applies here. The gradient is not necessarily flat at the endpoints, but because we have multiple variables, we also can't check endpoints because there are an infinite amount of endpoints on the constraint function given in the problem.
Uh-oh. What do we do then? The stupid constraint function is the problem. That's what's making this an absolute extrema problem instead of a nice and easy relative extrema problem. I wish it didn't exist.
Unfortunately, I'm not that type of wizard. But don't worry, one property of a gradient vector that we can take advantage of is that it is always perpendicular to the tangent line of a function at a certain point, pointing into the mountain, if you will. And this, my friend, is where the magic happens. Since the constraint function is a level curve, meaning that one of the variables is a constant as shown here, its gradient vector will point in the exact same direction as the gradient vector at the original function's extrema, where the tangent line is also going to be flat. Thus, both vectors are scalar multiples of each other, which we call a Lagrange multiplier.
Oh, that's so cool. That means that we can just set the gradients equal to one another, separated by a Lagrange multiplier, and solve the system of equations to find out the candidates for the extrema. And we can just plug them into the original function to find the extrema after that, and we're done.
Indubitably. Now try an example, you will.
A set of constraint equations are defined piecewise as x plus 2 squared minus y squared equals 1 for negative 1 less than or equal to x less than or equal to 0, and x minus 2 squared minus y squared equals 1 for 0 less than x less than or equal to 1, and is not defined everywhere else. And we want to find the maximum area of the rectangle bounded by the constraint equations. So I think the solution to this would be, we can first and foremost let x comma y be a point in quadrant 1, and we want to maximize g of x comma y equals 4xy, where g takes in all such inputs x comma y, satisfying the constraint equations. And thus, the partial derivative of g with respect to x would be equal to 4y, and the partial derivative of g with respect to y would be 4x. And using the Lagrange multiplier lambda, we can equate 4y equals 2 lambda times, in parentheses, x minus 2, and 4x is equal to negative 2 lambda, in parentheses, just y. And x minus 2 squared minus y squared equals 1, of course, is the constraint equation. So this is 3 equations, 3 unknowns. Solving this using a calculator would yield 2 solutions. And typing that in, we get x comma y equals 0.6341 plus or minus 0.9306. But we can discard the solution with a negative y value due to how we defined x comma y, and we just get 0.6341 comma 0.9306 is our only solution. Plugging this back into g gives us our final answer of g of 0.6341 comma 0.9306, and that would be equal to 4 times the 2, which gives us 2.360 units squared as the maximum area of the inscribed rectangle.
I've tried everything, but Lagrange multipliers are just impossible.
I think I might have found something.
Really?
It looks a little sketchy, but it might be a good option. It's called ChatGPT.
I've heard of this. Back in home, it's known as the mathematical dark arts.
Yeah, I hear it's only used in the most shameful of places, like EP stats.
A disturbance in the force, I sense.
We can memorize this stuff so easily.
And nothing can stop us.
The great evil has been summoned. Summoned by God, I have been returned to him. I must.
Master, I know what I must do, but I know not if I have the strength to do it.
The method. Lagrange multipliers. You must.
I got all the problems memorized now. We got this in the bag.
Yes. What are you prepared to do?
It's time.